Oh, thank you very much for your interest. Yesterday too, we discussed for hours. That keeps me young, huh? You remember, first we discussed quantum mechanics, and the main point to remember is the axis, the x operators were commuting, and t was very funny, it's a parameter in quantum mechanics, parameterizing time automorphism. But never, it was, so to say, never asked the deep reasons behind. It worked, and it works for really a beautiful range of energies, so to say. Now then we went to free fields. And first we did a little bit operator stuff and solved the equation of motion. It's all completely trivial. Finally we went to Weidmann distributions, ground state expectation values of these operators. And I mumbled a little bit about properties. Third, I went to Schwinger functions. Well, if that is the Weidmann distribution, I explained a little bit how to analytically continue in time differences and so on, go to tubes. And we came to the Schwinger function. And I gave you explicitly the S2 and also the Sn, I mean, which is trivial to get. But I didn't tell you, which is called Mindl's theorem. There exists a unique measure, Gaussian measure, centered measure, such that the expectation value, I mean the averaging over that measure of the two-point function gives you exactly what we had. And also for the n-point function. This measure, in a formal sense, is written by physicists, if you allow me. It's written by d phi, e to the minus, and it's supported on distributions, of course. On distributions S prime over R4, which we discussed yesterday. We had to smear, okay? E to the minus. And of course, you have to be very careful with these expressions, but it's just the action of a free scalar field, which we had yesterday too, anything like this. So, of course, here we had this discussion about how to define it in a sense of sequences of Gaussian measures, okay? And actually, I will reverse it in a few minutes. But it's good to know that this free measure is, so to say, there. And the main question is to perturb it. So to say, we would like to add here, except normalizations and so on, of course. We would like to perturb. That would be the final goal, like this. That would be great, yeah? Unfortunately, despite so much mathematics and so on, the poor physicists, what are they doing? They are expanding in this little lambda and say, oh, let's assume it's tiny and let's expand. Okay? If you really expand, I will not proceed now because I would like to save time. Well, what do you get? It's fairly trivial. Completely naive. Of course, now you have really, you see, what do you get? You get moments of a Gaussian measure, which I gave you. I mean, these are the dots here, okay? I can write, but everybody knows, yeah? Wick contractions, a lot of term. And if you calculate term by term, what do you get? Infinities. Everybody knows. Now, great people invented something. Freeman Dyson, who is still alive, by the way, I heard him speaking more than 90 years old recently, and he was among the inventors of renormalization theory. And he said, that's a method which will last for half a year, just the time needed to get something better. He underestimated this. Okay. but I have to tell, of course, renormalization went in various directions, and I will from time to time maybe say a little bit. Here, order by order, as formal expansions in this coupling constant, you can make sense of it. BBHZ should be called for, I mean, at least Bogolyubov in his old book, Barasyuk, his publication, Klaus Hepp was the first who used this iteration of these two people, that's an iteration scheme, to prove order by order all the endpoint function will have coefficients, removing the cutoffs is allowed and will give finite contribution. So that's a theorem, that's a deep theorem by Klaus Hepp, and Zimmermann, Wolfhard Zimmermann, found a kind of forest formula behind, and which led to Kohn-Kreimer Hopf algebra and so on. So it's fairly well understood. It would take a little bit more time here, of course. As I said, I gave a semester lecture to learn it myself, more or less. I mean, it's hard work. Okay, fine. But, so you put cutoffs and so on. By the way, I mean, one thing which I will do later on, I have gotten only two constants, the m and the lambda, but I have three operators, so better scale, so to say, the magnitude of phi, so you get a z square here, you get a z square here. Oh no, I said, I have put the square root and the z square here. Now you have gotten three constants. These three constants, lambda, m square, and z, are the bare constants. And all what you have to do is to, you see, maybe a few minutes. I'm sorry, I shouldn't spend too much time. For instance, the first contribution you get the Feynman graphs is such an integral. And naively speaking, in momentum space, we know what is a propagator. We had it yesterday. It's this one. Then some momentum is coming here in. That is to say, it's here 1 over p plus q square plus m square. And the rules are integrating over all loop momenta, so it's t in 4 dimensions. I mean, in 2 and 3, it would be finite already. Over p square plus m square, p plus q plus m square. Of course, that's even for physicists stupid, so we put a cutoff. Okay? And see, it goes like a log of lambda. And that's a contribution to a 4-point function, and as you will see, would see in 4 dimensions, to all orders you have such divergences appearing. So as I said, you can readjust all the 3 constants step by step and prove as formal power expansions that's okay. Huh? So I refer to such theorems. But what about the convergence? And the convergence of this expansion, well, I should write divergence, is of course not only questionable. We are convinced, well, it will not converge as a Taylor expansion, it will not converge as a Borel expansion, and so on and so on. And the names connected to it will come next lecture and lecture after the next, running under renormalons, under Landau ghost problem, and so on. And from time to time we will refer to it. So that's a big problem. So we have no model where everything is controlled, well, except a model which with Reimer we have pushed very far. But okay, it's also a toy model, which I will lecture the next two terms here. That's, so to say, our main goal, to have really a non-perturbative treatment. So perturbation theory is beautiful on the one hand, but of course not suitable to get really construction of an interacting field. Well, yes, that seems to be the case, but no, but then you have infinite number of asymptotic expansions which have the same non-analytic contributions, are not controlled. You see, it's clear at lambda equals 0, you have a non-analyticity, and you know all these kind of non-analytic functions, we have no handle at all. So it's ill-defined, I would say. That's the point. That's the point. No. Otherwise, that's exactly. Yeah, but yes, of course. But you see, like for instance, somebody asked same question yesterday in quantum mechanics. Of course, if you have a splitting between two eigenvalues, it's not a convergent expansion because it's a non-perturbative, it's an essential singularity around, but I have a handle to construct it, quantum mechanics. I give you upper and lower bounds. Nobody knows here how to make sense of QED. And it's even worse, I would say. Well, I don't know, I can give you many arguments. But so to say, the physics is already wrong. What does it mean? Lambda, for instance, we start, well, in electrodynamics, of course, lambda is replaced by alpha. Alpha is this beautiful constant of nature, which seems to be small. But the coupling constant depends on the energy. That's the point. I mean, a physical 4-point function in this case, yeah, so to say, should describe the coupling constant, and that's energy dependent. So loop corrections will change this alpha. So if you go in energy high, the coupling constant will increase. And if you go higher and higher, it will increase, and at the end it will become infinite. I will give you this argument maybe in next lecture, I guess. That's best. So we start with something small, but we evaluate it and get out, it's becoming big. So it's wrong. It's a strongly coupled problem. So therefore, QCD is much better, as we discussed, because at tiny distances it becomes free. So then the coupling constant runs to 0. Here the renormalization group shows that this coupling constant goes to infinity. So we started with something completely wrong. That's the problem of Landau ghost, as I will discuss. Yes. Yes, very good. Yes, thanks. Yes. 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 Very good. Yes, very good. That's Dyson's argument, by the way, when he was very young. Yeah, the coupling constant, well, in E squared too. You see, in QED, it's even more strange because it's really E squared in minus E squared, which means E in IE. So the ground state decays. I mean, it's not stable at all. Or you can even discuss very simple. You see an integral of one parameter. Well, let's call it lambda. That's, of course, a trivial example. Minus lambda x to the 4th. What is it? Well, it has a cut. That's your argument. At lambda negative, of course, it's becoming infinite. So the expansion, everybody can expand. 0 to infinity minus lambda to the n. And some moments, everybody can calculate gamma function, completely trivial. So how to reconstruct from these moments this function? It seems to be uniquely determined, isn't it? But you can, it's not a Taylor convergent expansion. But here it's very simple. You go to Borel summing the stuff, yeah? You have enough analyticity, somebody else has to prove, and it's not complicated, that you have enough analyticity in a certain region, and so on, and that the coefficients don't grow too much, the Taylor coefficient, these ones, so that it's Borel summable. It need not be, I mean, the functions themselves has a cut here, right? But it is at least has enough analyticity and so on. People tried, of course, but there are these Landau ghosts and singularities still around, and they don't kill it. Nobody knows how to kill it. I shouldn't say there is no summation procedure. Nobody found a suitable procedure, which is physically, in addition, makes sense, so to say, I mean, except for free fields. Okay. But it's, of course, also a good argument to see that for... So, I switch now subject, but please stay for some minutes at least. those who don't like the subject, I like it, of course, very much, otherwise I wouldn't do. Can think about it, how is it related to what I told you up to now? So how to call it, well, spin models. Of course, I don't have enough time to tell you all the beauty about this subject. It's very simple. Well, my historical favor is always to think about the simplest case. In 1925, that was before quantum mechanics was established, a German professor, I have no Austrian analog, unfortunately, at that time, Mr. Lenz, asked his student Ising to study a model, a statistical physics model. Ising, who is always called Ising by the Americans, okay? So, his PhD was solving the model I will write down in 1 dimensions. And first of all, it took too long, so young people should hurry up. And second, the teacher was disappointed. He didn't find a phase transition. I can't tell you why, but okay, at that time, you know, they knew there are magnets, you can magnetize, and you can switch the magnetic field, and then you hear a little bit. So they thought something could turn around, Barkhausen effect, or what is it called? This could be spins, but there was no spin. I don't know what they named it, but anyway, I mean, we call it classical spin now. And we start with a hypercubic lattice in d dimensions. Very simple. Well, solving is not everything is simple. Sorry? Hypercubic lattice, which means, well, let ik be integers, let's say from 1 to L or whatever, and I, is a multi-index, which is I1 up to ID, and I put a little a, and as we agreed yesterday, constants are sometimes 1, sometimes so a is a lattice constant, and I will put it to 1, but of course sometimes I will say, let's go to 0 with lattice constant or so, then we have to put it or so, no? Anyway, now, so that's a lattice, 1 to D, 1 to D, L I called it, sorry, 1L in 2 dimensions, for instance, but it doesn't matter, LL. So to each such a lattice point, I assign a variable out of 1 minus 1 and call it a spin, classical spin, up and down. So like the computer, a bit stupid. Quantum computer can be formulated, of course, too. It's a bit more complicated. Now, so this set of SIs, I call a spin field configuration. And now comes the definition of the model. An energy has to be defined. And the energy, let's take the following of this. There are in number, of course, 2 to the n configurations, and n is L to the d. And of course, you have some boundary conditions and all this. That's all, how to say, simple stuff. Now, what should be the energy? Well, the simplest case you can imagine, nearest neighbor interactions, let's say. So we sum over spins, Si is j, and we take only pairs of nearest neighbors. So this one interacts with the nearest, and so on. 2 dimensions at drawing. Okay. I put a minus to make it ferromagnetic, and of course the sums are, everything is finite. And then I switch on a magnetic field and couple all the spins globally, magnetic field, but you can make it locally, of course. I can write HI, that doesn't matter. Now, I follow the canonical ensemble. So there's a partition function as a function of the external field and inverse temperature, let's say temperature. Finite number of degrees of freedom, everything is finite, and it's very, very simple. Over all spin field configurations, we sum, that is to say 2 to the n possibilities. And it's just e to the minus beta h. Very simple, canonical ensemble. And of course, derivatives of the log makes a closed diagram. Derivatives with respect to h, for instance, make magnetization as a function of h and t. Second derivative makes susceptibility and so on. And derivative with respect to t makes the energy and the maybe u. And the second derivative makes specific heat and so on. So all thermodynamics we defined already, finished. Now, typically, canonical ensemble is nice because it's analytic function, but n going to infinity. And the question is, where are the singularities showing up? Some singularities show always up. It's not a constant function. The free energy, for instance, is defined like this. And okay, you take free energy per particles and the limit n going to infinity. And I'm claiming this free energy as a function of h and t will have singularities. Where are they? Now the question was, of course, for Mr. Ising, was in d equal 1. This is enough for his thesis nowadays. Now what do you do? Well, almost it's enough. Zn is a sum over one spin plus minus 1, the second spin plus minus 1, and so on. But it's always the same. There's a translation invariance in one direction. That means everybody, from what I wrote somewhere here, these two things, can write down a so-called transfer matrix, interaction from one spin to the next, and so on, up to the last one. And that's obviously the trace of t to the n. T is a 2 times 2 matrix. Everybody can solve this. And therefore, you take the larger eigenvalue as a function of h and beta. And look where it's singular and where it's not singular. Now, what came out for what is called the spontaneous magnetization? I'm sorry, limit h going to 0 from one side. You see, h breaks a C2 symmetry, up-down symmetry, and that's a kick. It's like an unstable equilibrium, and you either are kicked into one ground state or in the other, or you are in ground state anyway, and then it's smooth. So if you kick, h being positive, is the limit here. What did I write first? H. What did I write first? Just this one. It's called the spontaneous magnetization. And the phase diagram, well, we have in mind, it's clear, but what came out is the following. Spontaneous magnetization as a function of t. Well, you start with all the spins showing up and switch on temperature. So at the beginning, at temperature 0, you have a pure state here. You have a pure state here, all being down. These are these two pure states. Now you ask, what about finite temperature? Now nothing happened for poor Ising. Why? You know this? Who knows it? Never? Yeah, you, okay. Yeah, yeah, aha, so very good. I see it. This I didn't know. Yeah? He guessed. I see. Oh, poor guy. Did he pass? Did he pass the exam? I see. So, well, first of all, of course, time is running, yeah, the real time. It's very easy to argue, by the way. To argue why there is no phase transition in one dimension. Well, I can give you the argument. Maybe for discussions at tea time, then you can ask. You see, I defined free energy. I defined internal energy as a function of n. And if you make the derivative of this equation, you get an equation which everybody has seen somewhere. This one. S is entropy. Okay? So to say, if you erase here, which I will do later, it means increasing of energy for me as a physicist, okay? Now, here, internal energy, there are two, what is a phase transition? Two competing effects, so to say. One is energy, which likes to minimize everything. Therefore, I have put a minus. That's the most essential minus here. So one spin likes to have the others pointing up too. If you make a plus here, it's antiferromagnetism. Then they wouldn't align like here. Okay. It's Néel ordering. Okay. Now, that, so to say, tries to minimize energy, but that's entropy. And who wins? The minus sign is essential. Now, if you start with such a pure state, all pointing up, how much energy does it cost to have a chain of, let's say, n half spins flipped? Well, almost no energy. I flipped only two guys, this one and this one. So 4 times, they put a coupling constant here in front, 4 times J, so to say. While, what is the entropy? So delta F, that's the question, is delta U minus T delta S. How often can I do this? N half times. Well, n times everywhere in the periodic chain. So it's log n. And log n wins always. So it's always disordered immediately. That's a picture. In 2 dimensions, I didn't know, poor Ising. I should read. In 2 dimensions, that doesn't happen. As Peierls, Mr. Peierls told us, you see, if you have pluses everywhere in a square lattice starting from 2 dimensions, then you have islands of minuses, but here I have to draw what is called a Peierls contour and count. And here I will see, no, now also this contribution is not constant. It's, of course, also log n, and there's a competition. And there's always a temperature below. There is a kind of ordered state, and the picture is really this one, which you have seen, Curie temperature and so on, MS and so on. And here you come, one pure state, H going to 0, and here you come, H going from the other side, okay? And that's a mixed phase. Okay, so far so good. So you see it's a very nice subject, I would say, but the main question is, so the exercise for you, I tell you a little bit about this subject still. How is it related to what I told you yesterday? That's a big question. And you will see it's very easy. The answer is, of course, very easy. By the way, because you said in 2 dimensions he asked for the same effect, if you go to continuous spins, he would be right. And then it's a theorem, okay? A deeper theorem already. So if you have continuous, that's a discrete symmetry, up-down. But if I replace SI by SI, let's say 1, up to SI, I don't know, M, then M equal 1 is Ising, M equal 2 is a plane rotator, and has a phase transition. It's called Kosterlitz-Saulis phase transition. It's a C infinity. Non-analytic, but C infinity transition, by the way. Very complicated. And M3 is called the classical Heisenberg model. And this one, and all the others, are have no phase transition. Well, no, I'm sorry, now I'm mistaken. No phase transition, but the spontaneous symmetry magnetization goes to 0 if H goes to 0. That's a theorem in D equal 2. So there might be a phase transition, but the higher one, I mean, that's unclear from the theorems. That's called Mermin, Wagner, Hohenberg, and in field theory, Coleman theorem. There is no Goldstone boson in 2 dimensions, so that's old stuff. But in higher, yes, in dimensions D bigger than 3, of course, the continuous spin models and these models have phase transitions. And by the way, in D equals 3, it's fairly simple to prove. Well, there are are many ways to prove such things. In d equal 2, I have to give many stars. How many did other people give? To Mr. Onsager, because he solved, of course, a two-dimensional Elise model without magnetic field explicitly. And what did he do? He used more or less this strategy, like here, except, you see, you go in one direction, but you have a second one. So this matrix was, of course, a big one, I mean, which are called L times L matrix, extension L. And L goes to infinity. So he had to diagonalize really this big matrix, which he succeeded using Clifford algebra. That was in 44. I mean, that's, of course, a star among all the solvable models. It can be done in public, let's say, I don't know, an hour or so. But it's very nice. I mean, better, or it's much easier for me, at least, to go to fermion representation, but Clifford algebra. He did it first like this. And that's a star among everything. Maybe because yesterday there was, they were mentioning, conformal field theory. I make a remark in a few minutes. Now, well, D bigger than 3 and higher, it was possible to prove the existence of phase transition by famous people using reflection positivity, OS positivity. But I will, so to say, due to time, skip this kind of proof because it's a bit a different subject and we don't need for the rest. No, one-dimensional, yes. No, that goes like, vaguely speaking, a one-dimensional quantum spin is as complicated as a two-dimensional classical spin, and so on. So two-dimensional quantum spin, don't touch it. No, don't give it to a student. Three-dimensional Ising is a big challenge, and people like Claude Itzig and many people try to handle it by some method, whatever. Monster algebras, blah, blah, blah. Who knows? Who knows? Who knows? No, that's the point. Sure. Beautiful. Well, it's a beautiful subject. You know it. This one, I'm sorry, that's a sad. That's the most complicated model. I mean, more or less. No, there are many models of this complexity. But well, XXX is a classical Heisenberg model, okay? One-dimensional spin chain where really spins are, and you have spin waves and so on. You have beta ansatz, it was the starting point also from this side, right? Then, of course, XZ, that's the origin of quantum groups. You know, I'm sure. Yes. All these deformations, the little parameter between these two is called, well, Q. no, it's called cosine, some angle or whatever. It's Q plus Q to the minus cosine of some angle. So this parameter was a deformation parameter which led to this chain. And well, it leads to all kind of mechanisms, algebraic beta ansatz and so on. But Baxter solved Elliott Leaper did contributions to the, well, he did the XY model, okay? But the XYZ model, that's a big challenge to get the deep algebraic structure behind. But the phase transitions are known, yeah. Mm-hmm. I know it by heart, everything about this one. These are elliptic functions, so you have to watch a little bit. Okay. Yeah, sure, they have phase transitions, but only one-dimensional changes. So now, let me tell you the following, a kind of general result. So you see, we spoke about, in these classical spin models, for instance, about the two-point correlation function. You take second derivative, connected part, which means subtracting expectation values. Then it's known that this correlation function behaves, if I put I and j far apart, like what? That's called clustering. I spoke yesterday a little bit about clustering. clustering. How do the correlations cluster if I take them far apart? In general, it's not so easy to prove such clustering theorems if you don't have a trick, so to say. But it's more or less, it should behave like a free Green's function. And it behaves like exponential of minus I minus j over psi as a function of temperature, like constant, as long as t is not Tc. So we are, so to say, in bigger than 2, bigger than 1, I mean. Or at t equal Tc, it behaves like this one, b minus 2 plus eta. Now, as I told, I mean, the proof is really a kind of clustering theorem, and these expansions are always a bit unhandy in public, but okay. So what does it mean? Well, 1 over psi, psi is the correlation length called, and it defines, so to say, the point is, at the critical point, at this region, there are big fluctuations, which means instabilities, obviously, because it depends how you approach this kind of singularities. That's called the critical point. And the behavior at the critical point is very essential and will tell us a lot about the system. Now, the correlation lengths in so-called second order phase transitions will diverge. As you see, I mean, more or less, the transition from here to here means it diverges, and then the sub-leading behavior, which is this one here, away from the critical point, will jump. And eta is called a critical exponent. Well, there are many critical exponents, but I don't introduce all of them. That's critical exponent. And psi will diverge as you approach, like this one, and nu is another critical exponent. So I have at least introduced 2. Now, for Ising, since you can solve, eta is a quarter, nu is 1. All the others, alpha, beta, gamma, are rational numbers. So that is a mystery. For many years it was a mystery. And that comes from conformal field theory. That comes from representation theory of Virasoro algebra. It's the lowest level in the discrete series of the Virasoro algebra. So the anomalous dimension is 1/8. Each field has 1/8, so it gives a quarter. And so on. So at the time when Belavin, Polyakov, Samologikov classified the and Katz, Victor Katz, found all the discrete representations explicitly, people had more critical exponents, more results than models. But then Andres, Baxter, Forrester found to each of these discrete things a model again. Now, not all models are solvable in the sense that all correlation functions are known, all the CFDs and so on, but yesterday it was mentioned, so I wanted to tell you this mystery was really a mystery for a long time, because in 3 dimensions, these numbers are known under quotation mark. Heavy, heavy calculations are behind. But of course, there are no rationals. Nobody knows. I mean, you can look it up to 4 or 5 digits, yeah? But nobody knows what the stuff is in the 3-dimensional Ising model, for instance. So that's really a deep subject, and it's very hard to get this kind of critical exponents, for instance, more explicitly, except when you have a very good idea behind, like Ken Wilson, who learned renormalization theory in field theory and went then to this critical phenomena and got a Nobel Prize, because it was a method to get at least some expansions, non-trivial expansions, for the evaluation of this critical exponent. Now I should say, I will skip a little bit the details of higher dimensional situation, the explicit details, but the 4 plus epsilon dimensions I might still mention. So if you take the model, no, I'm sorry, I have to tell you, did somebody solve my puzzle? Oh, I'm sorry, I have to solve my puzzle. How is it related? I didn't tell you up to now. Ooh, time is running. I didn't tell you how is it related, all what I told you, to what we are doing. We are not doing Ising model. We are doing phi to the fourth. But everybody has heard the answer, I'm sure. They belong to the same universality class. And how can I justify this? The critical exponent of the Ising model and of the phi to the fourth model are the same. The point is, and that was Ken Wilson who pointed this mainly out, of course Kadanoff and these people were before, but he pushed it and used really renormalization group, which he learned from Gell-Mann, Loh, Stückelberg, Petermann, and these people were earlier, of course, but not using it in the context. So how it's connected? Well, I erased anyway, but you know this integral which Massoud doesn't like. We put a lattice cutoff and write it explicitly. Connection to connect to phi to the fourth model in any dimension, of course. Now, what do we do? Well, okay, integral d phi j, product over j, out of some volume, lambda, and some density, e to the minus. Well, we can even make it like this one to simplify. Maybe I write delta phi j square minus lambda phi j to the fourth times e to the, well, I write e to the minus to simplify phi I minus phi j squared over nearest neighbors. Everything is finite, I mean up to n, we said. Here the product was up to n. And maybe I make, to get all correlation function, a generating functional. So that's a generating functional and degrees of freedom, everything finite. J, well, and a few constants around, okay? That's phi to the fourth on a discrete letter. No, I'm sorry. I'm sorry, that is a discrete Laplacian. That is that's a constant, well, it's m squared, okay. The point is, I plot now the following. Yeah, it's a constant, and I didn't have space enough. And here you allow me to add a constant in addition. And I plot now this kind of measure. It's e to the minus a potential, okay, of the phi j. And I plot this potential a bit biased, of course, as a function of this coordinate. But as a parameter m square, well, I called it delta or so because I even would like to make it negative. So imaginary mass, but who cares? I mean, so it looks like this, if phi to the fourth, if m square is positive. But it looks like this one if m square is negative and the constant is adjusted. I mean, sorry, this should be the generate minima. Okay. Now you see, if you plot now e to the minus v of phi, how does it look like as a function of phi? Where it's very big here, it's 0. And where it's concentrated at these 2 points, it's big. So it simulates a delta of phi square minus 1, which is the Ising model measure. So I find this kind of for lecturing maybe not so bad to tell you. So as a function of the parameter, of course, only in the two-phase region, which is this one, These are the two peaks which give us the two magnetizations, the two pure states, localized here and there. But obviously, it's the same universality class in the sense of realization. Okay, so this you might believe, hopefully me. But it looks more or less the same depending on the parameters. And the critical exponents are independent of these parameters, so I can put them as you like. Now that's just for illumination. That doesn't mean that we have any precise results about the behavior. But in T bigger than 3, continuous or T equal 2, there exists a phase transition. So, for instance, in T equal 4 plus epsilon, you can try to scale to the critical point. That's a standard mechanism. You see very easily from our exponential behavior, that approaching a critical point means there is an infinity showing up. That is to say, the lattice constant, now it's coming. These two I combine to something that, you see, these are numbers. So the lattice constant is really a constant which depends on a dimension. So I keep such things fixed. I have to fix always something, and then I make a limit. So I have to make this limit where a goes to 0, and that means psi a of t in the limit t going to tc has to diverge, has to become infinity, which is okay. I mean, in these models, there is a second order phase transition, so it's fulfilled. You approach this critical point, and then you can study even the continuum limit. That's the point. I mean, a going to 0. Now, if you do this in a model in 4 plus epsilon dimension, you will realize that the 4-point correlation function, I make it like this. I make the lambda depending on the coupling constant, and I can prove, well, I was not involved in the proof. If a goes to 0, the coupling constant goes to 0. But I'll prove it next time, so to say, indirectly. That first proof has been done by Eizenman, Michael Eizenman, and later a little bit different by Jörg Fröhlich. And that goes along the triviality of phi to the 4th. But I will give an argument, next time on this issue a bit more detailed. Some questions to this beautiful subject. At least I feel it's a very nice subject, a bit more rich, because somebody asked me after the lecture yesterday, we spoke about it. You see, it was very, very much essential. Oh, I erased this, of course, that I took ferromagnetism. So statistical physics models are much richer, but only for ferromagnetism I get Osterwalder-Schrader positivity. Okay, this I have thrown under the carpet, for instance. So quantum Euclidean quantum field theory regularized corresponds to ferromagnetic spin systems. Okay, this people liked a lot, but nobody succeeded in really establishing existence of this limit in d equal 4. And why? Well, because you have the renormalization order by order behind. That's, so to say, a simple interpretation. Now, ways out. There are probably more ways out than I can tell you. As I told you yesterday, all these cancellations in supersymmetry and so on. I was good friend with Julius and Bruno Zumino, but it didn't really lead to a model which is constructed yet. So ways out, we start and go to the next subject, and which means we try to deform space-time. That started after Alain Kohn pushed it in 86, is it right? Yeah? Okay. 84. Well, the first non-commutative geometry long paper, 84 maybe, no? Sorry, 81? Oh, I see. Oh, I was influenced a bit later when he read Schwinger and Feynman. I don't know, that's probably number 6. Space-time. Now, first, maybe you allow me, I did a lot of physics already. Should I make a physics remark in addition to space-time? Where young people should be shocked and discuss a lot. That's the following. It's called the Bronstein diagram or so. I don't know. I don't know. I've seen it somewhere. You know, we have two really fundamental constants in nature, h bar and c, which I always put 1. I mean, that's the best. So, and here they are. Maybe here h bar, here 1 over c or so. What it means is, so to say, it's symbolic only. Yeah? That means here we switch on h bar, here we switch off. That means here this is classical physics. That's quantum. That's relativistic physics. That's non-relativistic, and that's relativistic. And in that direction, let's make a G. Or, of course, in the back of mind, you can make other coupling constant. We will make a theta. Theta will be the deformation parameter. And all the corners of this cube are now kind of a physics lecture. And since I almost told all of them, I was a bit surprised seeing such a cube. And the claim is space-time in all these corners is a bit different. Well, different, maybe it's similar in some corners, right? Yeah. But it's very funny. I mean, that space-time we treat in various lectures completely different. Now, what do we mean by, for instance, well, this one is, of course, my great favorite. It's relativistic quantum mechanics. It's quantum field theory. And here the fields, as we told, X and T are on the same footing. They are parameters, by the way. And that's at least a kind of compromise, a very good compromise. Now we go non-relativistic, that's quantum mechanics. That is, I told you, T is a parameter, X and P are the operators. I mean, that's really a funny world, yeah? That's a relativistic, that's GR, probably. Let me see, where am I? I didn't think much about it recently. It's relativistic and no quantum mechanics and classical. Oh, no gravity, here's gravity, GR, yeah, which I'm not so in, so I didn't know that's a corner. Then you have, of course, non-relativistic. Okay, that's quantum. Where are we? It's GR. SR, special. Okay, no gravity. Right, no gravity, special relativity. Classical field theory. Classical field theory, okay. Well, and so on and so forth. You can discuss yourself, yeah? And you will see that's, of course, a big challenge. GR, no coordinates preferred. Oh, that's very funny. So this line, for instance, our friends from loop quantum gravity try to go. It's, of course, much better to go this way, as you know, as I tell you, I mean, bottom up. Okay, and switching on G is very hard, so better switch on theta. That's, for instance, I guess, non-relativistic quantum gravity, which is also a bit strange. Not many people are discussing it, but it's nonlinear quantum physics. I mean, you know, they have nonlinearity is introduced. And that's, of course, classical physics, and okay, these are the dynamical systems. But space-time is always completely different. I mean, again, T is a parameter here, X and P are local coordinates of a manifold. So it's very funny, I would say. So how can we guess this kind of region here, which is 15 orders of magnitude away from the physics we are in? I mean, we really measure. Half a year, I would have said, we have no idea at all how to get information about this physics. By the way, and I was asked by our experimental colleagues to give a talk on all these questions, and I thought, how can I explain the non-renormalizability and all these funny questions? But then I found an excuse and told them, all this is an experimental question. We don't know gravity below a tenth of a millimeter or so. This question for going from here to here is so to say, you have to know what is gravity, classical gravity. I mean, Einstein's equations, they are beautiful, certainly, but not at tiny distance. It's not tested at all. So we are forced to have consistency ideas. And half a year, by the way, I realized I was wrong in the sense there was an experiment, BICEP2, which is of the order of the Planck length. So one never knows. One has to be very careful. And on the other hand, by the way, there is, of course, one discussion, should one quantize gravity at all? And the analog question in QED, in this region here, is like this. If you don't quantize the photon field, you get an inconsistency. It's a non-locality. That's called the Bohr-Rosenfeld argument. But unfortunately, it doesn't apply here in gravity because gravity is spin 2 and completely different. In electromagnetism, you can shield a field. You cannot shield a gravity field. So it's different and it doesn't apply immediately. So it's a question from the starting point, should we quantize? Now we, I mean, especially Reimer and me, we are not asking such questions. We deform space-time, take quantum field theory models over such deformed space-time and try to see what happens, so to say, how does it go on. Now, maybe a little bit history. Well, I told you already, 47, that was Snyder, who started this deformed Poincare Lorentz algebras. In the 60s, a few people tried to do a field theory on this, but they were, of course, not in Euclidean, but in Minkowski, and therefore they had all kind of problems. Well, the problems we have too, but a bit maybe simpler ones, okay? Now, of course, then, as I learned, it was already 81 or so, Kohn pushed this thing. And we were influenced over the years. I personally learned a lot from John Mador, for instance, together with Dubois-Violet, for instance. He had a beautiful differential calculus, and Richard Kerner, they worked on it, Robert Cockcrow, and so on. A number of people worked here on it. I entered in 92 when I learned from the fuzzy sphere and said, beautiful structure. Let's use it as a regularization of a quantum field. I probably will not speak much tomorrow about it. It was a starting point, and with people we went ahead. Now, somebody mentioned it maybe already in 94. Toplicher, Sergio Toplicher, Fredenhagen and Roberts did their analysis. And, well, they had commutation rules. Commutation rules among coordinates, which finally led to what I will treat too, and people treated before, of course, this kind of commutation rules, finally. I mean, it was a bit more involved because they considered the orbit of zetas under Lorentz transformations. Okay, that can be done, and we did too. Now, from here, but everything was in Minkowski space-time. Of course, we will do it in Euclidean space-time. The two people here had young people like Dorothea Barnes and Biancidelli, and they produced a lot of stuff in the next years, which led finally to what is called the mixing in Minkowski. I will tell you afterwards, I mean, next time. That's an objection against serious quantum field theory, so to say. Also, the subject was pushed a lot by Seiberg and Witten. I'm sorry, I forget, of course, names. I'm sorry for this. I mean, there are so many names around. But Seiberg and Witten influenced it a lot, and there was a boom then. Actually, this property was found at this time by Seiberg and Minwalla and Van Ramstok. and in Euclidean and in Minkowski, it was years later, analyzed a bit more rigorously, so to say. Anyway, I mean, that is a very rough thing, but we are all influenced by other people here in between, by the way, I forgot. And it's John Archibald Wheeler, which Sergio, of course, knew. John Archibald Wheeler, which had the, you see, but there are other guys like this guy, Mead, and what's here? Oh, I forget the names, I'm sorry for this. Anyway, already in the 60s, the 50s and 60s, the idea showed up that if you join quantum fluctuations, quantum uncertainties, and gravity, you will have troubles. I mean, the simplest argument is the following. Assume you have a lump, which is a distance d apart, localized in space-time, so to say. So how can you distinguish, or let's say, and I'm sorry, you have two lumps and they are a distance d apart, for instance. How can you localize? Is it one or two? So you should energy to it. And the energy needed is, of course, such that the wavelengths of the energy you put in, the energy has to be bigger than this one, okay? Now the gravitational constant enters in physics in a funny way. So I can multiply times this and get again a length. That's again a length. It's a Schwarzschild radius of this energy lump. And therefore you like to have such an well, these are inequalities of the order of magnitude, of course. And so you get a lower bound to localizability, which is square root of g, I guess, h bar over c cube or something like this, which are these fantastic 10 to the minus 35 meters, okay? And if 1 minute, oh, I'm sorry, if 1 minute or so, well, seconds even, if somebody says, he's cheating because he says, first of all, it's correct. I did it in the other lecture again. And in addition, you can get these funny numbers completely different by saying, I told you E square over h bar c is a constant, it's alpha. Now E square over r, everybody knows, is the Coulomb law. If the Coulomb law is gm square over r, the gravitational law, that's of course a kind of new physics entering, and that makes the Planck length. That makes the Planck length. So, which means if I divide now by h bar c, yes, h bar c, sorry, that's a number, 1 over 100. So what you get is a Planck length expressed in terms of, I don't know what, g h bar c or so. And that corresponds to this distance in Planck length, okay. So you have a Planck mass, a Planck time, and a Planck length. And at this extreme dimensions, so to say, physics will break down. And a model which has a little bit of this in it, I will discuss next days. Thank you.